let's start with number one here. For number one, I had two masses, and it doesn't say anything about friction, so we're going to assume there's no friction. All right. Um, Now, this mass, it just has one force. Well, it has one force that's pulling it straight down into the table. That's the weight, right? It would be the normal force. And then it's got a force that's the tension in the string that's making it slide across the table. Now, this force right here, the weight, that is not going to affect the motion because that force is going up and down and the block can only slide back and forth. And if there's no friction, then the weight doesn't matter of this block. So the only force that we have to worry about is the tension in this rope right here. And that's caused by the weight of the hanging mass. So the weight of that hanging mass, remember, is mass times gravity. If you guys don't have that equation written somewhere, make sure you write it down. Okay. Um, the mass of that is 9 kilograms. Gravity is 9.8. And so the weight is going to be 80, 89.7. Is that right?
88.2.
Oh, I was way off. All right, 88.2. 88.2 newtons. Okay, so the only force that's pulling these two guys is the weight of this hanging mass. And that force is 88.2. So when I look at the net force, right, if I was going to do the equation with all the applied forces minus all the opposing forces, I only have one applied force. It's the weight of the hanging mass. And I have zero opposing forces. There's no friction here. There's nothing stopping this or slowing it down. So that 88.2 is the net force. That's it. It's the one force that replaces all the other ones. But in this case, there is only one force, right? So it has to be the net force. So if I want to know the acceleration, I just do force equals mass times acceleration. The force is 88.2. And remember, you have to add the masses together. So it's not just the 9 or the 7. They're both attached to the same string. They're both moving together. So that would be 16 kilograms times the acceleration. And to get a by itself, you divide both sides by 16. So can someone tell me what that is?
5.51.
5.51 meters per second squared. Okay, so that was the easiest problem on the sheet. And the reason I wanted to do it is because it was the easiest problem, right? If you can get this, at least you can understand the basic concepts. So now, well, we might as well do problem number 2 as well because it just looks a little different, but it's really not. So in this problem, you guys, we have both weights are hanging off the pulley. So they're both getting pulled down. Right? Gravity's trying to pull both of them. Do you guys mind if I just make gravity 10 meters per second squared instead of 9.8? Will that bother anybody? No? Okay. All right. Some people get bothered by it. So I'm just going to round gravity to 10. So this would be 40 newtons pulling down in this direction. This would be 70 newtons pulling down in this direction, right? So if you think about it, if I look at this string, right, which weight is going to get pulled down? Is it the one on the right or the one on the left?
Right.
The one on the right. It's bigger, so this one's going to get pulled down. So it's getting pulled down with a force of 70, and it's getting pulled up with a force of 40, right? This one is getting pulled down with a force of 70, and it's getting pulled up with a force of 70. But in effect, you guys, what that means is that this whole system is getting pulled to the right, and the net force here is going to be the applied forces minus the opposing forces. This ends up being the applied force, the 70, because it will move to the right. And then the opposing force is going to end up being the 40. Oop. I'm sorry, this is just kind of going crazy all of a sudden. Okay, so the one force that would replace those two forces ends up being 30 newtons. And then if I want to find the acceleration, net force is mass times acceleration. So 30 newtons equals the mass of 11, because they're tied to a string. They're both going to move together, times the acceleration. To get the acceleration by itself, I have to divide both sides by 11. And so the acceleration will be 2 point what? 2.7 meters per second squared. So you guys, on your test, you can change gravity to 10 if you want. You can just round it to 10. All right, it makes the math a lot easier. Some people don't like doing that, so they'll always use 9.8, and I'm fine with that too, right? And if we were, launching a rocket into outer space, especially if there was an astronaut in it, we would want to use the most accurate numbers. But we're not doing that. We're just learning physics, right? So you can round it to 10 if you want. All right. So now at this point, is there any question that you guys would like me to do?
I have two questions. Could you do number 5, and then when for mass, is it only with the pulley ones you add it, and not like the other ones that we learned?
So you mean in problem number 5?
No, like if it's pulley problems, that's the only time we add the masses.
Right. So if it's a pulley problem, the masses are always going to move together because there's a string attached to them, right?
No string.
I'm sorry, say that again?
If there's no string, then you don't add the masses.
Right.
Okay.
Right. If there's no string, usually there is just one mass. And in fact, in number 5, there is only one mass here. Okay. So for number 5, I have a car. That car is getting pulled up a ramp. Okay. And the car has a certain weight. And remember, the weight points straight down into the center of the earth. There's a component of the weight that points directly into the surface. That's the normal force. That's going to contribute to friction. And then there is a component of the weight that's trying to make it slide down the ramp. And we call that the parallel force, right? So in this problem, you guys, it says how much force must be applied to the rope. So imagine that you're Superman or Superwoman, okay? And you're pulling on this end of the rope, all right? How hard do you have to pull to make the acceleration 1.8 meters per second squared, and the mass of the car is 1,300 kilograms? Now, if the mass is 1,300 kilograms, the weight is going to be 13,000 newtons if I use gravity as 10, right? I'm rounding gravity to 10. So I know the acceleration, I know the mass, I know the weight. Okay. Now, if I were to draw this car and just think about the forces that are acting on it, okay, I have three forces that will be acting on this car. I have the force that's my force pulling it up. That would be the tension in the rope. I have a part of the weight that's going to cause it to slide down. We've been calling that the parallel force. And then I'm going to have friction that's trying to oppose motion. Now, I know that friction is going to point down because I'm pulling the car up, right? So I can figure out this parallel force. I can figure out the component of the weight that's going to make it slide down. And I can also figure out the force of friction because we have those equations, right? We have them written down. So the parallel force, you have it written down as the weight of the object, mg, times the sine of the incline. And then the force of friction, you have that down as the coefficient of friction times mg times the cosine of the angle. All right. Now, actually, you guys, I made a mistake. I didn't read the problem close enough. In this problem, it doesn't say anything about friction, right? So we're going to assume that the coefficient of friction is 0, so that will actually go away. So we don't have to worry about this yet. So there really are only two forces. This applied force, that's the force that I'm pulling with, and then this parallel force, that's the component of the weight that's trying to make it slide down. So let's figure out what part of the weight is trying to make it slide down. Well, we said the weight was 13,000 because we made gravity 10 times the sine of the angle. So 13,000 times the sine of 35. Can someone tell me what that is?
I got a really big number. I got 745. I don't know.
Yeah, that sounds right. Hold on. Oh no, I got something.
I got 7,456.
Yep, I actually got that too. 7,456.5 if we rounded to tenths place.
If you use 9.8 before, because I did this before, the number would be smaller, right?
Yeah, that's right. That's right. Yep. So yeah, I'm sorry if you guys did it. I mean, if your number is close to this one, that means you did it right. So then the net force, you guys, that's going to be the applied force minus the opposing force. I actually don't know what that is yet because I have to figure out this net force first before I can plug it in this equation. And so I'll have to figure it out using mass times acceleration. I know the mass of the car, it's 1,300. The acceleration that I was given was 1.8. So 13,000 times 1.8, what would that be? Or 1,300, I'm sorry. I got it to be 2,340, is that right?
Yeah.
Okay. So then that is the net force. That'll go here. 2,340. That's the one force that replaces all the other ones. Then I'm trying to figure out how hard I have to pull. That's the applied force. And then I know that gravity, the portion of the weight that's trying to make it slide down, that's 7,456.5 newtons. Okay, so to get rid of this, it's being subtracted. I would need to add it to both sides. So if I add this, right, if I add that, then these will disappear. And the applied force is going to be 9,796.5. Is that right? Yeah. Okay. And this has to be a little bigger, right, than the net force. The reason it has to be bigger is because there's a portion of the weight that's trying to make it slide down that ramp. If I make the ramp steeper, then my applied force would have to be bigger. If I make the ramp less steep, then the applied force will be smaller. Right? You guys know that from real life, right? The steeper the ramp, the harder it is to use. The less steep, the easier it is to use. So is there another one of these problems that you want me to do? Anyone?
Four.
4? Okay. Four's a good one, because you have to use your brain here. So I want to find the mass of this box if the system accelerates at 6 meters per second squared. All right. Now I know the acceleration, 6 meters per second squared. And the mass of the whole system, you guys, I know is going to be 25 plus my mystery mass. So I don't know, I'll call this the mass of the system, the mass of the two. And then what else do I know here? I actually know the applied force, right? And the applied force is going to be the weight of this weight, the weight of the hanging mass. So if I just use 10 as gravity, it's going to be, the weight is mass times gravity, so it's 25 times 10. So it would be 250 newtons. So does everybody know how I got that? Yeah? Okay. Now the weight of this doesn't matter because there is no friction. If there was friction, this would be a little tougher problem, but there's no friction. It doesn't say anything about it. So remember, the weight of this box is pointing straight down into the table. If there's no friction, that force is not affecting motion. It's not in the direction of motion. So it doesn't have any effect at all. All right? So, oops. So when I look at the net force, it's all of the applied forces minus all of the opposing forces. There is only an applied force. There's only the weight of this hanging mass. So the net force is going to be 250 minus 0. Well, that's just 250, right? If there's only one force, it has to be the net force. So then we know that the net force is equal to mass times acceleration. So this will be 250 newtons equals, and then remember we have to have the mass of the whole system. So that would be 25 plus our mystery mass. And then we would times that by the acceleration, which is 6. Now there's a few different ways you could do the algebra, you guys. And that's up to you. A lot of you, I know from experience, you would probably take this and distribute it. So you would take the 6 and times it by 25, and then you take the 6 and times it by m. I'm going to do it a little differently because it's going to make the math easier, at least for me. If I divide both sides by that 6, it's going to disappear from that side, right? Do you guys see that? So instead of distributing it, I'm just going to get rid of it right away. So 250 divided by 6, can someone tell me what that is? It's 41.
41.6.
So that'll be 41.6, and then that equals 25 plus m. Now I want to get rid of this 25. It's being added, so you would subtract it. So if I subtract that right there, that disappears, right? And I would get m equals 16.6 kilograms. So the physics part of this wasn't too hard. The math part was a little bit harder, right? That required a little bit of thinking. But this problem, number 4, it's actually pretty close to number 1, right? It's almost exactly the same. It's almost exactly the same thing. You just had to find that mystery mass in there. Is there another one off the sheet that you guys want me to do? No? You're all good?
Do you have like the answers? Like
Do I have the answers? I actually, I thought I posted them, but I might not have. So I don't. Do you want to just do? Do you want to do number 6 together, and then I'll make sure that I post the answers for number 3.
yeah.
Does that sound good, you guys? Okay. So we could have just a little bit of practice doing this with coefficient of friction. All right. So for this problem, okay, we have a block and it's sitting on this ramp. Okay. Part of the weight, a component of the weight is going to try to make it slide down the ramp. Okay. Remember, we've been calling that component the parallel force. The weight of the hanging mass over here is going to try to pull it up the ramp. Now, until we do these calculations, I actually don't know which way this system is going to go. I don't know if this box will slide up the ramp or down. If this box slides up the ramp, then this parallel force will end up being an opposing force. If the box slides down the ramp, this parallel force will end up being the applied force. And this would be the opposing force. Okay? So we have to figure that out before we can figure out which way friction is pointing. Does that make sense to everybody? Okay, so the weight of this hanging mass right here, remember the weight is mass times gravity. So the weight of that hanging mass is going to be 7, and then we'll just round this to 10. So that'll be 70 newtons. Okay, so we have 70 newtons pulling down on this end. We have to figure out what portion of the weight is pulling it this way. So this parallel force, remember, that's going to be the weight times the sine of the incline. So that would be 10 times 10 times the sine of 14. Can someone tell me what that is?
$24.2.
Yep.
And then I have a question. So when you do parallel, you use sine, and then when you do frictional force, you do cosine?
Yeah, that's right. And the reason that you do the sine and cosine is because the weight is pointing straight down like this, right?
Mm-hmm.
And then the perpendicular force, or that normal force, that's pointing straight into the surface, and that parallel force would be this component, or this part of the triangle. So that force and this force, they're the same. And this angle and this angle, they're the same. Those are similar triangles. So then that parallel force is that opposite side. The normal force will be the adjacent side.
Oh, okay.
Okay. So then, So right now, you guys, we actually know which way this will go. Because this parallel force is only 24.2 newtons, this box is going to slide up the ramp. Now, don't get confused. Just because this box is heavier than this box doesn't mean it can't slide up. The reason is this ramp has a pretty small angle. It's almost, it's not exactly like being on flat ground, but it's closer to being on flat ground than it is to being dropped, right? So not much of the weight is actually causing it to slide down the ramp. More of the weight is pushing it in to the ramp. So we've got 24.2 pulling it down. This will end up being an opposing force. We've got the weight pulling down over here. That'll end up being our applied force. And then we're going to have friction. Friction will have to point this way. And the reason friction has to point that way is because the box is sliding up the ramp. So now we can use our equation for friction. Remember, the force of friction is mu times the weight times the cosine of the angle. So make sure, you guys, that you have these written down somewhere. Right? Make sure you have them written down. So then friction is going to be, mu is 0.227. The weight is going to be 10 times 10. We're just rounding gravity to 10. Times the cosine of 14. So we got to plug that in our calculator.
22.02.
22.02 newtons. Okay. So friction, 22.02. So I've got a portion of the weight pulling it down. I got friction trying to stop it. And then I've got this force, the tension in the rope pulling it up. And that's 70 newtons. Right? That's our applied force. So when I look at the net force, that's all of the applied forces, all the forces trying to make it go faster, minus all the opposing forces, the ones trying to make it go slower. And so this would be 70 newtons minus 24.2 minus 22.02. And if I plug that into my calculator, it's like 23.78. Can someone tell me? Is that right?
Yeah.
Yeah? Okay.
Yeah.
Okay, so that's the net force. And now I can finally find the acceleration. So F net equals mass times acceleration. This would be 23.78 equals the mass. Remember, they both move together. They're tied to a string, so I have to add them. 17 times the acceleration to get a by itself. Divide both sides by 17. And the acceleration will be 1.4 meters per second squared. Okay. Now, I cannot make a problem harder than this. This is the hardest possible problem you could get on our test. Okay? And I know this stuff isn't easy, you guys. I admire the fact that you're still trying, that you're working on it. Right? Don't give up on yourself. Just keep doing your best on all these